Alright, and we're back with part 2 of this video that I did not mean to be a 2-part video, but I had some microphone issues, the rest of it was just really bad, so we're going to go over the questions from the TNReady item release in this part of the video. It is storming and thundering and lightning here, so I apologize for the background noise, and there's a good chance that I might lose power, but if I do, I have plenty of battery, so we're going to keep going on and just see what happens. So here we go, first question. 24. It says that gravity is a force that pulls objects down toward our surface. Which two statements explain why a student standing at the top of a step stool does not move forward? So let's analyze these. Number 1, the step stool is a barrier that blocks the gravitational force. All right, kiddos. So answer choice number 1 has just told you if you have ever wanted to experience the feeling of weightlessness or be able to float, you need to invest in a step stool because it totally cancels out gravity and its effects. All you have to do is plop yourself on a step stool and you can just float away. Yeah, I don't think I even have to explain to you how insanely wrong that is. Moving on to the next one. The student exerts an upward force on the step stool equal to the gravitational force. Almost. Not quite. Think about what a step stool is. The step stool, you literally step onto it. That means your force is going to be pushing down on the stool because gravity is pulling you down. In order for you to exert an upward force on the stool, you would literally have to be under it, pushing it upward. That's not happening here. Let's try again with 3. The step stool exerts a force on the student in the opposite direction of gravity. I like that one because as the student is standing on the step stool, pressing down on it, the stool is exerting the normal force, pushing back up on the student. Hence the reason we have a balanced force and you can stand on something. Number 4, the student's mass is not large enough to be affected by gravity. This is all sorts of wrong. Your definition here with gravity, any object that has mass has a gravitational pull automatically, regardless of how big or small the object's mass is. Anything with mass has a gravitational pull. So this cannot be true at all. And our last option, the step stool exerts a force on the student equal to the force gravity exerts on the student. Love that answer too, because the step stool is going to exert that upward force to balance and cancel out the downward force gravity is going to exert on the student. That way they can coexist as balanced forces, which means your correct answers are going to be answer choice number 3 and 5. Moving on to our next question, which is 29. It says, which statement is true about the forces involved in an ornithopter and a pterosaur taking off? You may be sitting there wondering, what's an ornithopter and what's a pterosaur? And if you are, that's completely and totally okay because this is one of those questions that it gives you a ton of information, some which is useful, a lot which is useless about these two topics. So we'll scroll back up and look at the info it gives us, and don't worry. This is one of those test-taking strategies. They will throw big, crazy words at you for no apparent reason other than to throw you off your game and make you think that you don't know what's on this test. Don't fall for it, okay? Don't panic. It's going to be okay. Let's go look at the information that it gave you and see if we can figure out the answer to this. All right, so here we've got our information, and it tells us up at the top that fossil evidence of prehistoric animals called pterosaurs. All right, there's a pterosaur. It's a dead thing. That's all you need to know about it, literally, to answer this question. And the principles of Newton's second law help develop robots with wings. These robots, called ornithopters, assist with tasks like package delivery, blah, 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 blah. All right, ornithopters are robots. Again, all you need to know about them. So let's look at the next paragraph. Since this is dealing with forces acting on an object, it says, lift is the force that allows both animals and ornithopters to overcome their weight and take off from the ground. Thrust is the force that allows animals and planes to move forward horizontally while overcoming the opposing force of drag. And yeah, those are our main forces it touches base on there. So let's look at our little figures here. We've got a free body diagram that we talked about. So lift is our upward force, thrust is forward, drag is moving against motion, and then we have weight as our downward force. Some of you may be wondering why weight is there and gravity is not, since we used gravity in our free body diagram on the PowerPoint. Well, if you will think back to the Mr. Edmonds song, weight is the measure of gravity's pull on the object. So they have weight there as a measure of gravity. I did not assume the Naruto runner's weight in the PowerPoint slide, so I just threw in the normal force of gravity. And let's go back to our question, see if this has given us enough info to answer it. Which statement is true about the forces involved in an ornithopter and a pterosaur taking off? Thrust resists the motion of the pterosaur and the ornithopter. We should know from the little paragraphs that that is not true. Drag is going to be what moves in the opposite direction of thrust and resist motion, very similar to friction. Answer choice 2. Drag acts only on the ornithopter and not on the pterosaur. This isn't going to be a good answer choice either because forces are not going to select randomly and arbitrarily what they interact with and what they don't. If it acts on one, it's going to act on the other under the same circumstances. So this is not a great answer choice. Answer choice 3. Lift is the single major factor in the forward movement of the ornithopter. At first glance, this one sounds good, but read it carefully. It's saying that lift is the forward movement. If you look back at your free body diagram, lift is the upward movement. Thrust is the forward movement that we're looking for here. That's what's going to make this answer choice not true. And then you have the last answer choice. Gravity acts on both the ornithopter and the pterosaur. Well, duh, they both have mass, so they're both going to be subject to gravity's pull. This is our correct answer here. Next question is question 32. Which of these statements can be inferred from the data provided by figure 4? This is another question that it gave you a ton of information to try to figure it out. So let's go back and look at the information they gave us and see if we can figure it out from there. I do hope you guys are paying attention to the test taking strategies I'm doing right here. I'm reading the question, then I'm going back and looking for the information. Since they're trying to make this test mimic the ACT so much, they're going to give you way more information than you need to answer this to try to take up your time, overload you with information, and throw you off. Read your questions first, then define specifically what goes with your questions, and you'll be a much more efficient test taker. Plus, you'll probably have some extra time to go back and reread stuff if you need to. But don't get bogged down in trying to read everything first because it's going to be a little bit of a waste of time, and more than likely you're going to be overwhelmed and forget what you read anyway. Looking at this, figure 4. Up here in this first paragraph, I can see figure 4 shows the wing loading of some modern birds. Wing loading varies by animal species. Small, lightweight birds, such as sparrows, have a lower wing loading amount than much heavier birds, such as an albatross. Pterosaurs were known to have wingspans at least 3 times the size of the wingspan of an albatross, and have supported more than 30 times the weight. So we've got something called wing loading, and we are dealing with weight here. So if you're like me, and you aren't an ornithologist, aka a bird person, let's see if this tells us what wing loading is. And it conveniently does. Second sentence here. Wing loading is defined as the measure of the relationship between the elements of wing design and the weight of the animal. Wing design versus weight is what wing loading is. Now let's go to figure 4 and see how it relates to our question. Okay, so here we have figure 4. We've got cruising speed as one of our labels. I'm going to assume that's similar to the cruising speed of a car, which means that it gets to a speed and it maintains it. We have weight. We just established what weight was. It was the measure of gravity's pull on the object. And then we have wing loading, which we now know is the correlation between wing design and weight. Another test taking tip here. Read the labels. Don't try to get bogged down in automatically analyzing everything going on because they throw a ton of information at you in a diagram like this. Read the labels, read the title, go to the question, see what you're going to have to pick out from the graph. Don't just try to take it all in at once because, again, you can easily overload yourself and psych yourself out. So let's go back to our question now. Which of these statements can be inferred from the data provided by Figure 4? Number 1, the forces of weight and cruising speed have major influences on the, that should say wing loading, not wind, my bad guys, of a bird or an object. Well, if you just think of the definition of wing loading, weight is part of its definition, so that is a major factor. Cruising speed, however, was nowhere in that definition. Also, if you look at cruising speed, it varies. You've got two different cruising speeds with birds of very similar weights here. So it doesn't look like there's a direct correlation here. They all seem pretty clustered, kind of in the same little group where this cruising speed is not influencing either of these heavily. So I'm going to mark that one out and say no. Second answer choice. Wing loading is influenced only by the weight of the flying object. We know that it is influenced by the weight of the object and its wing design. So that seems partially right. Let's double check the other ones and make sure. Wing loading has no influence on the ability of a bird or an object to maintain flight. I'm just going to go ahead and automatically rule that one out because it is literally weight versus wing design. You cannot have a bird with the weight of like 50 pounds and little tiny bumblebee wings on it. It just doesn't work that way. And then last, the forces of drag and weight probably have no influence on the wing loading of a bird or object. Again, this is just a bad answer choice. Weight is literally part of wing loading's definition. So if we go back and look at Figure 4, since this question is specifically talking about information just from Figure 4, weight does seem to be the biggest contributing factor here to wing loading. Okay, this y-axis is where you see a huge, rather steep incline or slope. So weight is going to be your main contributing factor, so the answer to this one is B. Our next question that goes with the standard is actually the next question, number 33. It says, which statement would best describe the successful takeoff of an ornithopter that was designed using the model of the pterosaur? So we need to figure out what a pterosaur model is, and then looking at the answer choice, looks like in every one of these we are dealing with thrust and flapping, either slow and steady or rapid of large or small wings. Because a lot of times when the answer choices are identical except the change to just a few little words, just key in on those few little changes and look for those. So let's go back to the information that they gave us and see if we can figure out what it's going to be. Our second paragraph is going to tell us about pterosaurs. So we're wanting to talk about initial takeoff. And right here, let's see. Liftoff at the beginning of flight required a pterosaur to push off with maximum thrust. So we need maximum thrust as part of our answer choice, using both its legs and wings. Second, the initial takeoff and the maintenance of altitude was dependent upon rapid, prolonged, and efficient wing flapping. So we need rapid wing flapping here. And I think that may be literally word for word one of our answer choices. So let's go back and check it out and see if that's all we needed. Notice they give you this big, huge, giant paragraphs, and you only needed a few sentences out of each one to get these right. So, takeoff, ornithopter designed after a pterosaur. Minimal amount of thrust, we already know is wrong. It needed maximum thrust, which means this is not a correct answer and this is not a correct answer. So we already took out half our options. We needed powerful amount of thrust. And this one says rapid flapping and rapid flapping, but this one has small wings and large wings. So we kind of overlooked that. Let's go back and see if we can figure out whether it has small or large wings here. We're looking for the word wingspan here. So here we go. Pterosaurs were known to have wingspans at least 3 times the size of the wingspan of an albatross, and were believed to supported more than 30 times the weight. So big wingspan then. Let's see which one had the big wingspan. That is going to be our last answer choice here. We've got powerful thrusting, rapid flapping, and large wing. That is your correct answer choice on this one. All right, guys, so those are all the questions on Newton's first law of motion. Again, that is an object at rest will stay at rest unless acted upon by an outside force, and an object in motion will stay in motion unless acted upon by an outside force. Hopefully you're able to learn something from this. Sorry I had to be split into 2 parts, and sorry that my mic's acting up on me a little bit. Better luck in the next video, and see you then. Bye.